Hello, my name is John and I'm with Far From Standard Tutoring, and in this video I'm going to explain acid-base chemistry. So the first thing you need to know for acid-base chemistry is the difference between Lewis acid bases and Bronsted acid bases. So for Bronsted reactions, I drew up the generic theme here, the general base and the general acid reacting. I'm going to first compare that to Lewis acid and Lewis bases. So a Lewis base has a source of electrons, like this NH3 here. It has a non-binding electron that can bond to something. And our Lewis acid has an open shell site somewhere, which we have in this BF3 here. The boron has an open shell, which can accept electrons to make a bond. So the product of a Lewis acid-base reaction is just a complex, where we're going to have the nitrogen bonded to the boron. And it'll look something like this. There's just a complex formed, and charges will be present because we're changing the form of charges and what the things are bonded to. So the boron will now have a negative charge, nitrogen will have a positive charge. If you need a review of formal charges, see one of the previous videos about formal charges. So whenever you do a Lewis acid-base reaction, you're always going to get a complex, okay? Now this is different than the Bronsted acid-base reactions, okay? Just like we had a Lewis base, a Bronsted base is also a source of electrons. But instead of where in the case there was a Lewis base and there's open shells, a Bronsted acid just has an H. Okay, it's just a source where an H is and a proton can be formed. So there's a transfer of protons, and the reaction will be that this base will take off the H and leave a new acid. Okay, so the purposes of this video is to more or less rank how acidic an H is. Okay, and how we can find the acidity of acid strength. So what I have here is the general acid, and you can find the acidic strength of it by looking at the strength of its internal base. So the stronger the acid, weaker will be its base, okay? It'll be more reactive here, it'll be less reactive here, and if it's more reactive, that means it's going to be more unstable. And so it's going to be stable when it's weaker, okay? So if it's stable, it's not going to want to react with anything else and pick back up an H that it just gave off, okay? So if it's more apt to give up an H, it's going to be less apt to pick it back up, okay? So how do we evaluate the acidity of an H? Well, there's a general scheme here that I've written. Here's the H, and the direct atom that it's bonded to affects how the H can fall off, and more downstream, resonance can also affect the acidity of an H, more or less how quickly an H will fall off, okay? So if we first look at the atom directly bonded to the H, there are 4 criteria that can really affect how quickly that H can fall off, and therefore how acidic that H is, okay? So we have the size, we have formal charge, we have hybridization, and electronegativity, okay? These all affect the electronic pull from that atom, and therefore leaving that H to fall off pretty easy. So for example, if that atom is pretty big, comparing that to an atom that's smaller, that H is farther away, and it's going to fall off easier. Also with electronegativity, if there's a higher electronegativity pull, that H is farther away, it's not being pulled so much as the electrons are, so that charge and the H plus is going to fall off easier, okay? So this general theme, these 4 criteria are pulling electrons. Therefore, the H plus is easier to fall off and it's more acidic, okay? So I've written up here the periodic trends for acidity, right? So along with that atom that causes electronegativity to affect the H, you have the general theme between like the nitrogen and the oxygen, right? Oxygen has more electronegativity than the nitrogen, therefore more acidic, okay? The H is going to fall off easier from the oxygen than the nitrogen. So let's look at a couple examples here. We have CH3CH2OH, and the only difference between that one and this one is that it's CF3CH2OH, okay? So instead of an H here, we have an F. F is fluorine, of course. F is more electronegativity, has more electronegativity than the hydrogen, so it's going to pull those electrons more so, okay? That's called the inductive effect. And therefore, this H downstream is more apt to fall off easier, okay? So this second molecule here, this is more acidic than the top one here. All due to the electronegativity of the fluorine, and it's called an inductive effect, okay? Let's next compare these 2 molecules. We have the same atom that it's bonded to. The H is bonded to the O in both cases. And then farther downstream, they're both bonded to a carbon, okay? The only difference that we need to look at is what's going to happen if that H falls off. So let's have that H fall off, all right? We have a general base coming in to take the H, and the source electrons move back up. Same here. We're going to take the H, source electrons move back up. In the top case, what we're going to form is the oxygen is now going to have 3 lone pairs, okay? So the pairs of electrons move back up. We can't put those pairs of electrons anywhere into the molecule. There is no resonance, okay? But in the bottom case, there is. If we take off that H and move the lone pair up, we can move one of them in and then move the pi bond up to the other oxygen. So those electrons are delocalized between the two oxygens. There's movement, there's resonance, okay? Now resonance stabilizes this molecule. Therefore, the molecule is going to want to get to this state easier than this one. So this is more acidic, okay? It's more stable, so it'll give up that H easier to reach that stable point, okay? So that goes back to our theme here. It's going to be a stronger acid because it's less reactive when it gives off that H because it's more stable. And that's due to resonance, okay? So we can link together this example back to our theme here. Resonance induces a more acidic H, okay? So you'll see in our next video that we can use what they call pKa to also determine how acidic an H is, okay? So stay tuned for that if you want to learn more about acidity. Thank you for tuning in.